So Dr. Ransalu Senanayake is a postdoctoral research scholar in the machine learning group at the Department of Computer Science, Stanford University. Working at the intersection of modeling and decision making, he focuses on making autonomous systems equipped with trustworthy machine learning algorithms. Prior to joining Stanford, Ransalu obtained a PhD in computer science from the University of Sydney in 2019. He has been an associate editor of the IEEE International Conference on Intelligent Robots and Systems since 2021. So let's welcome Ransalu to deliver his speech.
Yeah, thanks for the kind introduction, Sankar. Let me try to share my screen. Okay, great. Do you hear me well and see me well?
Yeah, all good.
Okay, perfect. Great. So the focus of today's talk is how do we fail stress testing vision-based systems using reinforcement learning. So one of the reasons why I picked this topic is so that I can cover a bit of computer vision, a bit of decision making, and more about validating all these systems. So let's start with the video. Okay, so nowadays we have all these self-driving cars. They can detect objects, they can detect roads, lanes, and everything, but still they collide and still they fail. So let's try to understand some of the reasons behind these collisions and how to make these systems more trustworthy. So let's start with a typical computer vision task. Say we have this picture, and there are various vision tasks that we can do with this picture, right? So we can detect objects, for instance, like let me turn on my laser pointer. So we can say detect vehicles, pedestrians. Also, we can come up with some segmentation algorithms to segment crossings, roads, sidewalks, and so on. So normally, in most of these tasks, we use standard data sets. Sometimes we collect our own data sets, such as MNIST, ImageNet, and other data sets, and train our model. Right? So we have our data set. Say we use 80% of data for training and 20% for testing. So this is what we typically do. But is testing on a test set good enough? So that's my question. Now, this is an article published in The Guardian 6 years ago, why self-driving cars aren't safe yet, and some of the reasons that they give is rain, roadworks, and other obstacles. And although this is 6 years old, to date, most of these problems are not solved properly. That's why we do not have self-driving cars in the market, right? So when we think about all these computer vision algorithms, we really need to think about how we deploy them and why do we have all these algorithms. Just think about the deployment time. So we get data from real world and you send that data through the computer vision algorithm that you develop. So why do we have the computer vision algorithm? Because at the very end, we have a decision maker, right? If you are not making any decisions out of your computer vision algorithm, then probably there's no point of having a vision-based system. So when I say decision maker, it could be some algorithm. For instance, in autonomous driving, the decision maker is some kind of a control or decision-making algorithm. It could be as simple as a PID controller, or it could be like a commandeer MPC or a POP-DP or reinforcement learning algorithm, right? So that is decision making. or it could be a human. For instance, this is one of the works I found on the internet. So this is COVID-19 detection using X-ray images. I apologize, I forgot to put the reference here. And it showed then they apply some kind of an explainable AI technique to highlight which areas the clinicians should look at so that they can analyze more about this X-ray, so that they know that this is COVID-19. Right? In this case, the decision makers are humans. So no matter who the decision makers are, we have to make sure that our computer vision algorithms here are good enough and they don't fail. Right? So what do I mean by like failing? What are the reasons for failing? So one reason could be rare events. For instance, all of a sudden a kangaroo jumps in front of your vehicle. Right? So probably your computer vision algorithm has never seen kangaroos because kangaroos were not available in the training data set. So that could be one reason. Another reason could be disturbances. This is very common when we are trying to deploy any computer vision algorithm in the real world. One example is rain. If there is rain, I'm sure our computer vision algorithm will not work as we expect. It could be rain, fog, any other weather condition. So we need to find how and when our models fail. So the work today I'm going to present is based on this work from Harrison. Harrison is a PhD student. He will be presenting his work at this conference in Kyoto in a couple of months. So the running theme for today is autonomous vehicles. So I will quickly explain what kind of sensors they have. They have cameras, you can see here, just regular cameras. They have LiDAR. So LiDAR are basically some depth sensors. You can measure the distance to nearby objects. They have radar, you can get the velocity. Some of them have radar, and other like typical time series data, such as what you get from IMUs. I want to focus on this LiDAR. So how does the LiDAR work? It shoots a laser beam and it reflects back so that you can measure the distance using time of flight. So it's not just a single beam. In many LiDARs, you have like multiple beams. For instance, like 64 beams rotating around so that you can scan your entire environment. So for around like 100-meter radius. So what you see at the bottom is a sample of this like 3D point cloud. So these 3D point clouds, in terms of the resolution, they are not as good as cameras, but they are good enough. So right? You see some pedestrians here, some vehicles, and so on. But what happens when some kind of disturbance occur, right? For instance, all of a sudden it starts raining. Now, this is kind of an overly simplified example. You know, it does not reduce to 10 meters all of a sudden, but you get the idea, right? So when we have some sort of disturbance, we get noisy measurements, we have backscattering, the decrease the maximum detection range, and so on. Okay, so with that in mind, now focus on the vision stack in an autonomous vehicles. We have data, basically the point cloud if it is LiDAR. Right? The first thing we do is we need to identify objects. And we can use some of the state-of-the-art algorithms for object detection, such as point pillars. What you can see here is like these bounding boxes are the objects that you detect. Okay. Once you have these bounding boxes, you need to track those vehicles or pedestrians. So it's like a continuous process. Right? That's where the temporal component introduces into this system. Once you have all these traces of pedestrians or vehicles, then what you're going to do is you are going to predict into the future. Okay, if I observe say a pedestrian at a couple of places, then you want to predict where that pedestrian would walk or where that car would go in the next few seconds. Just think, when you are driving, that's what you do, right? You have a model of all vehicles around you in your vicinity, and you try to predict where they go. And based on your estimation of where they go, you make some decisions to accelerate, to change the lane, and so on, right? So we can output these future trajectories, then the decision-making algorithm can control the vehicle. Okay. So I'm basically going to focus on these three parts: object detection, object tracking, and object prediction. So when I say like prediction, trajectory prediction, you can see like in blue here, you can see multiple paths. All are possible paths, but one of them is more probable, right? But that's what's highlighted in green. So if we have some kind of disturbance to our data, say because of weather, some of the downstream tasks can fail. What do we mean by failures? So failure is something that you define. So it depends on the applications. For instance, in this application, so one of the downstream tasks is like object tracking. So I can define if the estimated position is, say, greater than 2 meters, then it's a failure. Or you can define track associated with the target vehicle is lost. So this ego vehicle is our vehicle, and say you observe you observe the vehicle for several time steps, and all of a sudden you don't see the vehicle, right? The vehicle is there, but your vision algorithm fails to detect it, right? So that can be defined as a failure. And for, say, trajectory prediction, if the final displacement error is greater than, say, 15 meters, that can be defined as a failure. Right? So all these things really depend on the application. For instance, so we observe the vehicle, and the vision algorithm predicts it would go just straight. But if you look at ground truth data, it has actually turned left. So there's a considerable displacement, right? So that is how we quantify kind of the failure. Okay, so we need to find how and when downstream vision tasks could fail. So if I tell a bit more formally, so we need to find a sequence of input disturbances in such a way that the downstream task could fail. When I say sequence of disturbances, it's basically shown in red here. So you have rain or you have mist. So if it rains in this way, our object tracking algorithm would fail. That's kind of the thing that we want to get at. So there are various ways that you can handle this problem. So one way is like adversarial attacks based on, say, generative adversarial GANs or something. But one thing we had to make sure is, remember that this is like a real system that provides some vision information to the decision-making algorithm, right? So they must be realistic. So whatever the adversarial attack we find, it should be realistic. But it's generally difficult to do with many adversarial attacking algorithms. Even if we can do, we need like a lot of data. For instance, like in rare events, it's difficult to find a lot of data. And most of these adversarial attacks do not consider this temporal nature that are inherent to some of these autonomous vehicle applications. Right? Just to show a common example that is very popular, say you have a panda, and if you add some noise, it gives you the result. Okay, classifies it as a gibbon. Right? In this case, what you are interested in is finding this noise so that it would result in a gibbon. The panda would result in a gibbon. Okay, so basically we are interested in finding this kind of noise, but more like they should be realistic and they should be efficient and so on. Now, another way that what we can do this is like say do some exhaustive search or do some Monte Carlo sampling. For instance, what you can see here is a like 8 LiDAR. Is it so you can see some LiDAR beams here, and we can just exhaustively search. Okay, if the rain drops here, this is my output. If the rain drops here in the next time step, this is what happens. Now remember, like we are looking for several time steps, and we have like thousands of data points in at a given time. So exhaustive search is not possible, especially given this temporal nature and the size of the point cloud. Even Monte Carlo sampling is not possible. It's not just tractable. Okay, so we need a smarter algorithm to find these failures. For that, we propose perception adaptive stress testing, or PAST. Okay, so consider we have a black box simulator S. So we have 4 different functions. So we initialize our simulator with some state S0. So when I say states, basically I will define later. Just consider they are just positions of the vehicle, so trajectories that we really do not know. They are just estimates. And then we have something called step, right? So steps. So this is the functionality of a step. The output of this step function is it returns the likelihood of transition from one state to another state. Okay, and so you have some randomness based on a pseudo-random seed A. Your objective is to find these disturbances in such a way that we find a failure. So your objective is to step through and find these A, or find these disturbances, so that you will end up in a failure. Basically, we want to find that failure. And if we find a failure, so we activate this terminal. If you go to the end, we find a terminal. If you find a failure, we activate this failure. So let me cast this into a Markov decision process, right? So in a Markov decision process, it's like a tuple of these 4. We have states, actions, pivot function, and transition. So the states are basically the perception system's belief state, or state estimate about the true state and future trajectories. So that's what we consider as our state space. And our actions, this is the most important thing. So actions are the actions the agent choose. Agents choose some actions. So those are basically the pseudo-random seeds for generating the disturbances to the input data. And we try to collect some rewards, and we have a transition function. So if you are at this state A, and if you take the action A, you go to state S prime. So if I show here, you are at S0, and if you take action S0, you go to state S1 and collect the reward R0. Then we are at state S1. You go to state S2 by, if you take state A1, also you get reward A1. So basically, we want to collect all these rewards, right? We want to maximize our sum of rewards. So this is how we define our rewards. If we find a failure, so we say our reward is 0. If we are not at the end, then we compute the log likelihood of taking that action. If we do not satisfy any of these two, we add a negative, it's basically a penalty. Right? So So if you're not familiar with reinforcement learning, so this is how you should think, right? So say there's a child and say a parent. If a child is, so if you want the child to achieve a particular task, and if the child achieves it, say you make the child happy. So that's the positive reinforcement. Okay. And if not, you punish. So it's not the best way, but so this is just like the analogy, right? So if you find a failure, we give more rewards. If we do not find, we punish. Okay, so now we want to maximize the sum of all these rewards. So sum of log BA means like if you want to maximize the sum of rewards, we have to maximize the sum of log BA, which means we maximize the product of all BAs, which means we maximize the log likelihood. We maximize the likelihood, just the product of BA. So maximize the total reward means maximize the likelihood of finding failures. Okay. Now, how do we maximize the total rewards or maximize the likelihood of finding failures? So basically, we had to find a policy that maximizes the expected utility given by the value function. So this is like the typical value function. You have a reward here. So this is your current reward. So you are not only interested in getting the current reward. So if you want to become a good planner, you have to think about what will happen in the next few actions as well, right? That's this part. This is kind of the discounted future. Okay. So if I take this action now, and if I take that action next, so this will happen, that will happen. So you have to kind of think ahead a little bit. And in this case, I'm not going to go into detail about like how to solve all these, but just to simply say we use a variant of multi-colored research to find the optimum policy. You could use any model trial technique. So basically, what we get out of this algorithm is a sequence of actions or disturbances. If I show this more pictorially, you have your LiDAR point cloud here, and say it rains, so that some of your points get disturbed or perturbed. So these perturbed points are shown in red. Okay. So now you send this through your perception algorithm, say tracking algorithm or trajectory prediction algorithm. You get some rewards, and using the MCTS algorithm, you find the disturbances. So because the way we cast this, because the way we define our reward function, we find the most likely disturbances. Okay. So that is what we really need. A sequence of actions or disturbances so that we find the most likely failures. So now let me clarify some of these using some experimental results. I'll quickly go through two experiments. First one is a simple example, finding failures of a single vehicle using a simple disturbance model. Now in the next experiment, I will use a real like a rain model, like a weather model, and show you what happens. We use some real data from the new scenes datasets. It has several scenes, and each scene is like 20 seconds. Okay, experiment one. So we are not interested in the entire environment. So this is just for explaining purposes. We just consider a target vehicle. What you see here in these like black dots, they are like the point cloud, and these squares are your vehicles, and these very dark regions are like some obstacles, maybe buildings. Okay. Now the very simple likelihood, very simple disturbance we consider here is this function. So this is like the, say for a given point, it's like the Bernoulli, whether you have that point or you remove that point. So you have a whole point cloud, you remove it or you keep it. Okay. So a random sample generated with seed A. So this is like the seed we have for all m points. So we have m points. we only consider target vehicle and we only consider points inside that. Okay. So we compute the Bernoulli likelihood, where n is the number of points to be removed. Okay. Out of n points, you're going to remove n points. So you can compute the likelihood. Just to explain this picture, so this is time. Remember that this is a temporal task, time 0, time 1, time 2. This is what happens when there's no disturbance. And this is our algorithm passed. And this is another baseline, ISO. And you can see there are two colors, black and blue. Blue is our detection and black is the ground truth. Okay, black is the ground truth, blue is the detection. And on the right, so these are like more visually meaningful images. So it's so just to summarize, I'm just considering just one of these images. Right? Okay. Blue is the detection, black is the ground truth, and these like little bars you can see on these inside these squares indicate the directions. For instance, the target vehicle is moving down because this little bar is directed towards the bottom. Okay. And as expected, there's always a little difference between the detection and ground truth. That's why they are not perfectly overlapped in most examples, most cases. Right? So let's go back to this picture again. So you have a bunch of these, and this is our target vehicle. This is what we need to focus on. This. Okay. So since we are only focusing on the target vehicle, I'll just zoom them. Okay. So it's the same images, but I'm just zooming in the target vehicle. So let's see what has happened. So at time 0, so our algorithm does not remove any point. If it removes any point, it will be indicated in red. Okay. In the second T1, it has not removed any points. In time 2, T equals 2, it has removed 15 points. So the removed points are indicated in red. So this is like in the ground truth means ground truth is the black. So this vehicle is coming down. Okay, we have black. So you remove 15 points from this point cloud, not just pick 15 randomly, but that's what our past algorithm gives. So just remove these 15 points, right? So what has happened? The direction has completely changed in the detection. So in the ground truth, it's going down, but if you remove 15, just 15 LiDAR points from this car, from the front, the computation algorithm confuses and it predicts, okay, it's going in the other direction. So what happens? So the ground truth is like this. It's going like this. This is like the future trajectories. But because our downstream task, the vision algorithm has failed, now it's predicting, okay, our algorithm, this vehicle is going in the opposite direction. Okay, so just think, when you are driving, if you confuse a vehicle, say it's like a random place, and if you confuse the direction of the vehicle, that's going to be catastrophic, right? You will definitely end up in a collision. So that's why it's extremely important to find this kind of failures. And this is like the baseline method. It is like what happens in this model is it basically removes like chunks of LiDAR points. You can see it removes a lot, and especially at the very beginning. So this is not really the behavior we want. We want to find the smallest disturbances, so that results in a failure, because they are the most critical. And this is like the more realistic example. Rather than considering that Bernoulli likelihood, now we consider a real physics-based weather model. So LISA is a rain model. So if you include a point cloud and if you define say a rain rate, it can give you the modified point cloud under this disturbance. So this is a physics-based model. It has certain probability distributions. So what we do is like we modify this LISA. That's why I call this LISA prime. still gets the point cloud and the brain rate. And because we have some probability distributions inside this LISA, we can compute the log likelihood. Rather than getting the modified point cloud, we get the log likelihood because that's what we need for the reinforcement learning model, right? And for experimental purposes, we say, okay, we consider heavy rain rates and light rain rates, and past should be able to pick. This is what happens when it rains like 20 millimeters per hour and so on. Okay. These are like just for experimental purposes. And you can just focus here. So red points are basically points that are perturbed, or these are the disturbances. Now we do for the whole point cloud. Just focus on this algorithm. So after T0, T1, T2, you can see like the trajectory prediction algorithm. There's kind of a huge deviation if you remove these points. Now think like if you try all the combinations, it's pretty challenging to find the most likely failures like this, right? So that's the importance of using some kind of a smart algorithm, say in this case like reinforcement learning, to find failures. Otherwise, we will not be able to find. So just not tractable. And if you look at like the distributions, okay, so past or red is our algorithm, and this is the log likelihood. And rather than sampling randomly, Monte Carlo is just random sampling. If we use this past algorithm, it's more likely that we find good failures. And yeah, so we computed the failure rates. Sometimes the failure rates is not the only important thing, right? For instance, like in some cases, ISO has a very high failure rate, but right, I mean, it's easy to find failures. So for instance, like if you remove all points, I mean, that will definitely end up in a failure, right? So what we need is not just finding failures that are meaningful, also like the finding failures that are caused by the smallest disturbances, because they are the most crucial and difficult to find. Okay, so we need to look at several matrices. To summarize, we propose an efficient framework to find likely failures in high-dimensional temporal vision tasks. And I would like to thank Harrison, who really worked on implementing this and getting this to work, and Masha and Bernard and Michael. So Harrison will be presenting this work at IROS. If any of you are attending IROS in Japan in another couple of months, so please visit this poster as well. Okay, so thank you. I think the time is up. Open for questions.
Thank you very much, Ransalu. That was a very interesting piece of work. So let me open up for questions from the audience first.
Hi, Ransalu. I have a quick question. A very nice talk, a very interesting work. So my question is, have you looked at whether you can use the your algorithm to complement different components of the system? Like, for example, if you can use your model or your algorithm to detect failures in the, for example, detection model and versus trajectory prediction model, and complement the failures of these models using your algorithm such that the overall system can get a better performance.
So when you say complement, what does that exactly mean, if you can clarify?
Yeah, so what I meant by that is, like, if you just look at the trajectory prediction model and that has a failure, and you can complement that part by using the information that you get from the, for example, the detection model. And that's what I meant by the complementing.
Right. So we do so we just look at prediction, tracking and prediction. So those are like the downstream tasks. So we can look at different modules for sure. But in terms of like, okay, so here what we do is like we try to find failures, but we are not looking at like after finding failures what we can actually do. Okay, that's like the next big piece I'd say. But yeah, good point.
Thanks. If there are no other questions, I have one more. So is there any specific reason why you are using Monte Carlo tree search instead of model-free methods?
I mean, okay. So one of the lab mates in our group, he tried different methods, and Monte Carlo, like using Monte Carlo tree search, it was much easier to find, and it's kind of efficient. That's the main reason. It's like basically for performance reasons, but like people can explore any algorithm.
Yeah, I was wondering if there were any scalability issues with like using a Monte Carlo tree search, especially if you have like more point in your point cloud, because I guess like Monte Carlo tree search usually suffers from issues with scalability. I wonder if you have any thoughts on that.
Right. So I'd say like any method suffers from that, right? Like so.
That's true. That's true.
Yeah. So, but like okay, so now this is like not like a very high resolution image. If you have a very high resolution image, that could be a problem. But this is a point cloud. So compared to like a sequence of like very high resolution images, this is slightly lower dimensional in comparison. So it was possible. And also it's not just like vanilla, it's not vanilla Monte Carlo research, but it's like this with this like double progressive whitening and other stuff.
Oh, I see. I see. Okay. Yeah. Yeah. Very nice work.
Thanks.